Welcome to this discussion of pump theory for reactor fluid mechanics. We're going to start with the angular momentum equation from our control volume analysis section at the beginning of the class. The basic idea here is that we apply a torque to the pump, and that applies a force to change the angular momentum and the kinetic energy of the fluid. Now we're going to simplify this equation by neglecting the surface forces and the body forces. Basically, we're going to assume that the flow is frictionless and that there's not a significant change in elevation. We're also going to assume a uniform flow and a steady state system. This helps us eliminate some additional terms. And what we're left with, we can integrate over the control surfaces. Now the front and back of the pump are walls, so the flow rate through those is 0 and the surface integral is 0. And that leaves us with two surfaces to account for. One is the inner surface of the rotor and one is the outer surface of the rotor. And we need to address both of those. And when we do that, we arrive at Euler's turbo machine equation, which relates the shaft torque that has to be applied to the pump to the mass flow rate and the inlet condition and the exit condition. Now, we have to talk about some sign conventions here. The tangential velocity, or V sub t, is positive when it's in the same direction as the blade rotation. We also say that torque is positive for pumps because it's doing work on the fluid, but negative for turbines because they're extracting work from the fluid. And we can figure out the tangential velocity using these velocity polygons that you see here, one for the inlet and one for the exit. So the value of u, which we call the runner speed, is the actual speed of the turbine blade at either the inlet or the exit. So that gives us this. And then w is the relative velocity of the fluid compared to the turbine blade or the pump blade. So here's your blade, your rotor blade, and here is your relative speed. So if this is your relative speed compared to the blade, and this is your blade speed, you can add these two vectors together and get the actual speed of the fluid. And then you can take the projection of that velocity along the u-axis here to get the tangential velocity at both the inlet and the exit. So once we've done this, we want to convert to work done because we're really interested in how much power we have to apply to this pump in order to add sufficient energy to the fluid. So we get that by multiplying by the rotation rate. The rotation rate, omega, is in radians per second. And so we can simplify this by recognizing that the runner speed, u, is just the radius times the angular speed. And so we end up with that second equation. So we can also modify this equation further to work in what we call head. Head has dimensions of length. This is very common in industry because length is very easy to relate to, and it's easier to measure than, say, watts. So in industry, you can put a vertical pipe attached to the exit of the pump, and the height that that fluid rises to is the head. And so it's very easy to measure. Finally, there's one simplification we can make for many cases. If we assume that the flow enters the pump axially, and that we can see here, the fluid enters the rotor axially with no tangential velocity from this left side, and it leaves through this section here, moving outward and rotating. So if we have no tangential velocity at the inlet, we can eliminate all the inlet terms from all of these equations to further simplify them. Now, this makes all the equations much simpler because now we only need information from the outer edge of the rotor, not the inner edge. But it's important to remember that this entire analysis is very idealized. We've neglected friction, we've neglected a lot of effects to come up with sort of an ideal pump. And of course, there's no such thing as an ideal machine, so we have some additional analysis to do. Now, we do have to make some changes to this analysis when we talk about axial flow machinery. Axial flow machinery doesn't require that the flow change direction to move from axial to moving outward. It continues to move axially, but the rotation rate changes. So in this case, both radii are equal, which means the runner speed is the same for both the inlet and the outlet. So we can remove the runner speed from inside the parentheses, and now we just need to worry about the difference in the tangential velocities. The process is roughly the same as it is for the centrifugal pump. We need to use the velocity polygons to figure out the tangential component of the velocity. However, we can't generally assume that there's no tangential velocity at the inlet. It's going to depend on the angle of the rotor blades and how they're built. The assumption of constant properties that is required to make this valid is typically okay if the blade height being the distance here from the bottom of the blade to the top of the blade, is less than 20% of the mean radius. So if the blades are relatively small compared to the total radius of your axial flow machine, then you can make the assumption of constant properties. So now we can take a look at this Euler turbomachine equation, assuming axial flow at the inlet. And if we include the definition of volume flow rate, which is basically area times velocity, right? We can substitute that in and come up with a new equation. So that new equation looks something like this, and it gives us the pump head as a function of the geometry, the rotation rate, and the volume flow rate. We wanted to get everything in terms of volume flow rate because it's much easier to measure than tangential velocity. So by doing some math, we were able to find a simplified equation that's more closely related to things we can directly measure. So then we can start analyzing this equation, and we can start by looking at the case where there's no flow. So if there's no flow, then the volume flow rate Q is 0. And this is what we call the shutoff head. It's the value that's produced when there's no flow. We can also look at some other situations. We can start by looking at 90-degree blade angle at the exit, which is what we call radial blades. And if that's the case, then the cotangent of beta 2 is 0. And so in this case, for an ideal pump, the head produced by the pump has no dependence on the volume flow rate. Now, this is not necessarily a totally realistic conclusion because, of course, there would be losses in a real pump that would reduce the head produced under certain conditions. So, again, for an ideal case, radial blades mean no dependence of head on volume flow rate. We can also look at the case of forward curved blades, where the blade is curved in the direction of rotation, or beta is greater than 90 degrees. Now, in this case, the head actually increases with volume flow rate. However, it's almost never used in practice, because this type of pump is very unstable in operation, and it's prone to cavitation, which is the creation of bubbles inside of the pump, and that degrades the pump performance and can damage the rotor blades. So there's a very high maintenance costs associated with this kind of pump. Almost all production pumps have backward curved blades, very similar to what's shown in the figure on the left side of this slide. This means that head decreases as your flow rate increases. And of course, these pumps do have to be correctly designed, but they tend to be much more stable with reduced cavitation and reduced maintenance cost. Now, in reality, there's no such thing as a perfect machine, so all pumps have some kind of losses. At low impeller speeds, you can have fluid recirculation, as we see in the figure. There's friction in seals and bearings, and there's friction in the fluid flow. And if the inlet flow rate and the pump rotation rate are not matched properly, you can have shocks and flow disturbances at the inlet to the pump, which can reduce the efficiency and make it less effective. So due to the complexity of all of these factors, we usually rely on engineering correlations and experimental data. So we need to make some definitions. First, we define the hydraulic power, and the hydraulic power is the actual rate that energy is input into the fluid. So it's not the rate at which energy is input into the pump, but the rate at which the pump adds energy to the fluid. Then the pump efficiency is used to relate the hydraulic power to the input power of the pump. So the hydraulic power is actually the energy that goes into the fluid, and then the pump power is the energy input to the pump. And the difference between those is given by the pump efficiency. Now, all of this information can be found in typical pump curves. So at first glance, these pump curves can seem very overwhelming. There's a lot of information here. But most pump curves are created for a family of identical pumps. The only difference is that the rotor sizes change. So here we have different rotor sizes from 5-inch diameter all the way up to 8.5-inch diameter. But other than that, they're all exactly the same design. And so they all have very similar curves. And you can see our typical head flow rate curve here for the 8.5-inch diameter, head in feet, and flow rate in GPM. And this is a curve that's very similar to the one for our backward curved blades that we just saw. Now, these lines show that bigger rotors produce more head for the same flow rate, which makes sense because since the radius is bigger, the runner speed at the exit will also be more. Now, we also have lines that indicate the hydraulic power. So these are lines of constant power. So you can see that if your operating point falls along this line somewhere, then you'll have a hydraulic power of 20 horsepower. And we also have lines that indicate efficiency. So this just shows that the efficiency tends to increase as you reach the design condition for the pump. So if we look at this 8.5 diameter line, you can see there's different efficiencies, and the efficiency climbs until you reach the design point for the pump, where the efficiency is around 73.5%. And then as you get further and further, you start to lose efficiency again because you're moving away from the design point. And that has to do with things like inlet shocks and friction losses and so on. So if we're looking for a particular head and flow combination, say we have a 400 GPM flow rate and we need 200 feet of head. So we go to our 400 GPM flow rate and we go up until we reach 200 feet of head. And we want to pick a pump and figure out what the system is going to look like. So here we can't use the 7.5-inch diameter rotor because it wouldn't produce either the flow rate or the head we want. So we have to move up to the 8-inch diameter rotor, and it's actually going to produce a little bit more head than we were looking for, about 230 feet instead of 200. So we would have to add, say, a valve or some other kind of flow restriction to increase the head loss in the system to match the pump head produced and maintain our 400 GPM flow rate. Then we can look and see it's just above the 30 horsepower line. So we're probably looking at about 32 horsepower for our pump power if you come down here. And we can also see that it's going to be just over 72% efficiency. So it's between the 72% and the 73% line. And so we can use that to come up with information about our pump and select a rotor size for a particular application.